your second video for 8.3 volumes. And we're picking up here with example 4. We have the region bounded by the graph y equals 3 times the square root of x over 4. The x-axis and the line x equals 4 is revolved about the line x equals 4 to generate a solid. Find the volume of the solid. So we're going to go through and sketch what this looks like. So I have this square root here, and 4 is going to be my important line, because 4 is going to be what I'm going up to. That's actually going to be my rotation line. Four is my rotation line. So I know that if I'm bound by the x-axis, if I plug in x is 0, I'm going to get back 0 for my y. If I plug in x is 4, because that's what I'm going to, I end up getting 4 over 4, which is 1. Square root is 1. I get 1, 2, 3. So that is going to be there. So this actually is kind of a curve that looks like that. So we are going to be taking this and we are going to be rotating it. It says around the line of x equals 4. So if I take this area and I rotate it, I'm going to get some kind of region like that. Now, this does not make sense to slice perpendicular to the x-axis because that is going to give us a shape called a shell, and that is not something that we are going to cover in AP Calculus 8b. However, if I flip this and slice it perpendicular to the y-axis, then that is going to give me a disk, which is something that I can easily find the area of and then find the volume of. So I know that, again, this is going to be, let me choose my words carefully here. I have 1, because I have my picture. 2 is going to be my area here. Well, my area would be whatever this unit is. So it's going to be, this is 4, and I'm actually going to go the opposite way with this one. Rather than going this way, I'm going to go this way, because that actually goes to my curve. So we need to be kind of careful here, because I do have 4 as my middle value here. This curve here is this equation that's up top, but I do need to put that equation in terms of x rather than in terms of y. So I'm going to solve that over here. I have 1/3 y is equal to the square root of x over 4, because I moved the 3 over. So then I square both sides. So if I square both of these, I get 1/9 y squared equals x over 4. And then I multiply by 4, so I get 4/9 y squared is going to be equal to my x. So 4/9 y squared, but that is going to be, I do have to take into account 4 from that, because the distance between those is going to be 4 minus that value, because that value that I found right here, that's actually this distance. So if I need to find the black distance, I'm going to have to take 4 minus that, and that's actually what I'm going to be integrating. So my actual area is going to be pi times 4 minus 4/9 y squared, and then again the quantity squared, because 4 minus 4/9 y squared, that is just my radius, and then it's pi r squared, so I have to square that. Again, this is the disk method, not the washer, so there's nothing to subtract out as far as the whole goes. In order to integrate this by hand, we will have to expand this binomial. And it's not going to be pretty. We can leave the pi on the outside for that. So I square the first term, 2 times the last times the first. So 2 times 4/9 is 8/9 times, well, negative 8/9 times the 4 is going to give me negative 32/9 y squared. And then I square the last term, so the negative 4/9 y squared, the quantity squared, is going to be 16 over 81 y to the 4th. So that is going to be my area formula. Not the easiest because we did need to change in terms of y, and then we needed to do 4 minus that value, because again, this red piece over here on the graph, that is going to represent the 4/9 y squared. So I do need to do 4 minus that value in order to figure out what the actual radius is going to be. So step 3, my bounds are going to be from 0 to 3, so at least that was pretty easy to figure out. And so now I have my integration, which is step 4. I am going to pull out the pi, and then I have 16 minus 32 over 9 y squared plus 16 over 81 y to the 4th power. Does not look like a 4. Let's try that again. And then dy. And then this is something that I can go through and integrate. So that's pi times 16y minus 32 over 27 y cubed, because again, I add 1 to the squared, and then I divide by the new exponent. Well, I already have a 9 there, so the 3 I'm actually just multiplying by the 9. And then the next one, I add 1 to the 4, turn it into a 5. That's going to get multiplied by the bottom because I have to divide the 16 by it, so that's going to be plus 16 over 405 y to the 5th power. And we are evaluating that from 0 to 3. Luckily, when we plug in 0, we are just going to get 0. So really, it's the plugging in of the 3 is all I really need to be concerned about. So pi times 16 times 3 minus 32 over 27 times 3 cubed plus 16 over 405, 3 to the 5th power. Let me separate these out so don't get confused with that. And then you do some algebra, you simplify that, you have the pi in here. So you end up with the fraction 128 over 5 pi, and this is going to be units cubed. Units cubed for that. So again, volumes using shells are not on the AP exam. If you are going out and seeking your own material to help you with any kind of understanding for anything that we've covered, please note that if the solution mentions anything about using a shell, shells are not on the AP exam for AB. I believe they are included for the BC exam, but they are not included for the AB exam, which is one of the reasons why I've skipped all the examples with the shells. So if you're watching the book video, you can go through and skip through those types of questions because you will not have to work through them. This is the last example we're actually going to go through and work out. I do have another example we're just going to talk about briefly, but there's no math to do in that one. So with this one, a mathematician has a paperweight made so that its base is the shape of the region between the x-axis and one arch of the curve y equals 2 sine of x. Linear units is going to be in inches. Each cross section cut perpendicular to the x-axis and then therefore to the xy plane is a semicircle whose diameter runs from the x-axis to the curve. So we have to sketch some type of picture for this, and then we're going to find the volume of the paperweight. So this would be our curve. So there's, goes from pi to 0, because I am in the x-axis, and I'm looking at, my equation was y equals 2 sine of x. And then when I cut these cross sections out of here, those are all semicircles. I know the first one kind of looks more like a loaf than an actual semicircle, but those are all semicircles. So step 1 is going to be my picture. Step 2, I know I have semicircles. Well, the area of a semicircle is pi over 2 r squared. So I just need to figure out what my radius is. Well, my radius would go from the halfway point out. This entire distance is going to be 2 sine of x, but if I'm taking half of that, because I need the radius for that, that's actually just going to give me sine of x. So my radius here is sine of x. Therefore, my area formula is going to be pi over 2 times sine of x, and then the quantity squared. So step 3, my bounds. Since I have to be bound by the x-axis, that's where I get the 0 to pi, because 0 is where that x-axis is going to start. I get back 0 there. And then pi is the next place where it actually crosses the x-axis. And then 4 is where I'm going to look at my integration. So I can pull out the pi over 2. I'm integrating from 0 to pi of sine squared x. This is not an integration you can do by hand. This is not an integration that you can go in and do any changing to make it work out to be something that you would be able to work with. So we are actually going to use the calculator for this, or at least for the inside part. So if you plug, notice I did pull the pi over 2 out. I'm going to multiply by that at the end, which is perfectly fine as long as you remember to actually multiply by that. So if I put in 0 to pi of sine squared x dx into the calculator using fnint, I'm going to get 1.570796327, and then multiply by your pi over 2, 2.467 inches cubed. Because it does tell me up there my linear units are in inches. So inches cubed is going to be what the volume is for this. This example, it is in your book on page 419. This is Cavallari's theorem. This just has to do with volumes and why it's not necessarily important how your volume is set up. What is important is what your endpoints are. So if you have some type of solid that has an equal altitude and identical cross sections, they have to have, let's see, I just lost my train of thought there. So if you have your solids and they have the same altitude, so it doesn't matter if they're leaning or completely straight up and down, as long as their heights are the same. So your altitude is going to be your perpendicular height, and their cross-section area is the same. Then they have to have the same volume. And it's this, again, this is on page 413. This is going to follow from your definition of volume because the cross-section of the area in your interval A to B are going to be the same. And the easiest way to illustrate this is with a stack of pennies. If you have a stack of pennies, let's say you have 10 pennies in a stack. Each cross-section is obviously going to be a penny, and the whole shape is going to be a cylinder. It's actually a right cylinder if you have it straight up and down. Now let's say you slide that penny stack so that it's kind of on an angle. Well, there's still the same amount of pennies. The height is still going to be the same, even though it's kind of going up at an angle instead of straight up and down. But you still have the same altitude, and if you were to slice that, you still get a penny as your cross-section, because they are the same. They are going to have the same volume, even though they don't look the same. So any solid that has the same cross-section and the same altitude, again, altitude would be perpendicular height, have to have the same volume. So that's going to wrap up our lesson on 8.3 on volumes. This is another one of those sections that typically appears in the free response questions section at least once as one of the parts of one of your problems. I have seen questions where they ask you to actually set up how you would find the volume, but not actually go through and find the answer. So please make sure you do focus on the setup and not just, oh, can I get the correct answer for this question? And we will look at some free response questions a little bit later on, and you'll see what that setup request would look like. So go back through, watch the first 8.3 video, rewatch this video, seek out anything else that you want to on the internet, on YouTube, on Khan Academy to help you, and reach out to me if you have any questions.